90 subtract the 10, I give you, that means what, 80? You said, Professor, 80 degrees is 10's complement. Try another one, thank you. If I gave you 23 degrees, I said, what is 23 degrees complement? Are you going to use the same routine? Just subtract it from 90. And I guess 90 subtract 23, I'm standing here trying to do it 67, I guess. So 67 degrees is 23 degrees complement. They must add 90. So if I gave you one, it was subtracted from 90. That's what this says. You're subtracting an angle from 90. In other words, you're finding this complement. And you're taking the cosine of it, and we saw before the break, that should be equivalent to sine of. So I'm using cosine with sine. I could have done this with cotangent with tangent, or cosecant with secant, all those CO words. So guys, I'd like to establish this. This considers what we're doing before the break. And what I'd like to do with your help is to, when I say establish, show those two sides now really, really, really are the same. Based on something we did earlier. I love making connections here. So if you see the word establish, give me an idea how you show me those two sides, Professor, are really the same. Okay, which one?
Yeah, cosine A minus B.
Love that. Love that. He's telling me, Professor, that looks like cosine A minus B. So why not use the cosine A minus B formula we had before the break? I know it's fresh for most of us, so you may not know the formula yet. But it's cosine A, in my case, cosine pi over 2, cosine B, which is theta, plus sine A, which is pi over 2, sine B, which is theta. I use the cosine A minus B formula that's on your handout. Also, I had on the board here. Beautiful. That's step one. And if I take a look at what was given to me, which is beautiful, I applied the formula on the left-hand side, which you saw before the break. Cosine at 90 on the unit circle. This takes me back to the unit circle. At 90 cosine, the x-coordinate up there is 0. That means that first term, if that's 0, it's going to drop out. 0 times anything is 0. Sine of 90, someone tell me what sine, the y-coordinate was up at 90. Who remembers the y-coordinate up at 90 on the unit circle, which is sine? Is that 1? And if I do my business there on the second term, that really says you have 1 sine theta. And altogether, you have that, and you've shown the two sides are the same. You've established that as an identity. And that makes a little tie-in with what we were doing before the break. There it is now, confirmed. We established it, okay? So I want to look at that with you guys. PK was doing some reading from the handout. PK, I know, I'm pretty sure there's some other formulas on that handout somewhere. You guys have the handout. Were there more formulas than just the sine A plus B, cosine A plus B, and all that business or not? None? Was there double angle somewhere on the back maybe? Oh, there was some double angle. Was there anything else on the front there besides the sine formulas, cosine formulas? Was there anything to work? The tangent, what was I asking you to do there? Oh my goodness, my goodness, my goodness. Here I was going to jump to chapter 7. Now see what has to be done. PK, thank you. Here we go. Guys, there's one on here that says, please, now we'll do it real quickly, sine of 7 pi over 12. And I want the exact answer, no calculators of course being used. And you're sitting on, or taking the final exam, you say, oh my Lord, I know 7 pi over 12 is not one of those on the unit circle. Now, can someone be clever and tell me, unless I give you a hint on the side, what could you do to find sine of 7 pi over 12 where there's a connection with what we've been discussing? you want to rewrite this as, Joseph, tell me again. Now, he says, Professor, rewrite, now we'll check and see if this will work for me. Rewrite that as that. Now, if I use a common denominator of 12, put these together, do a little check on that. That would be 4 plus 3, that's 7 pi over 12. That's 7 pi over 12 written like this. These two would sum up to, with the common denominator of 12, what he wants there. Now, he has placed this in the form of, look at that, sine A plus B. I did a cosine on this one. And that sine A plus B formula, guys, says sine A, which is pi over 3, cosine B, pi over 4, plus cosine pi over 3, sine pi over 4. I know your formulas. I hope that formula's copied down correctly. You guys were following. Did it copy down correctly? Now make replacements. He has taken me back to the unit circle. We keep on going back to that unit circle on all these problems. Sine, the y coordinate of pi over 3, guys, help me out. Is it what? Radical 3 over 2? Cosine of pi over 4, you refer back to the unit circle, is that? Cosine at 60 or cosine of pi over 3 is that 1/2? Help me out. And this is radical 2 over 2. Lord. Answer? Radical 6. PK, now if it looks like this, you can multiply them together. I think before the break we went to subtract a couple I had there. You can multiply. Over 4, and then plus down here radical 2 over 4, and you end up with this. All over 4. If we had a mistake there. You guys agree? Okay? Now, just out of curiosity, does anyone know where 7 pi over 12, you may want to convert it, in which of the 4 quadrants is it located? I should sketch it. Just the angle, just out of curiosity. Where is 7 pi over 12 located? Is it quadrant 1? Is it in quadrant 2? Is it in quadrant 3? Is it in quadrant 4? Is it in quadrant 3? Okay, quadrant 3. Hang on now. Let's go through this real quickly. Now I'm looking for 7 pi over 12. I know right here at pi, that could be written as what? 12 pi over 12. Let me squeeze that again. Is that true? And I know this is pi over 2. Just trying to get it. Some points there to work with. Pi over 2 is 90. Since I see a 12, it could be written as 6 pi over what? 12? So am I between 6 and 12? So am I in quadrant 2? That's where the angle is located. So I'm in quadrant 2. If I'm in quadrant 2, which looks like I might be, and I know from middle school, if I'm over there, please tell me, are those the coordinates? And what was I asked to find? Sine. And the y coordinate has to be what then? Positive. Did my answer come out to be positive? Is radical 6 plus radical 2 over 4 expression a positive answer? If I'm in quadrant 2, it better be positive. And it came out to be positive. I just want to check and see where it was and see if the sign works. But guys, the answer is radical 6 plus radical 2 over 4. PK, not too much more here, but I'm going to do something else I saw on there which has to be done right now. Oh, right here. It looked like, hang on, this. Number 2, I guess. On your handout, guys, this is all on your handout. Cosine 5 pi over 12 times cosine 7 pi over 12 subtract sine 5 pi over 12. Make sure I get all this copied down correctly so we can get through it. Sine of 7 pi over 12. Let me step back and look at it. Woo! Looks good, I think. Now, does anyone think they know what's going on here? Before we close this down pretty soon. And you know, 5 pi over 12, 7 pi over 12 are not on the unit circle. But yet, you see us staring at you on the final exam, no calculator, and then I want an answer. What is it? What are you doing?
Looking around formulas.
Is it one of the formulas? As a cosine, what was it, cosine A plus B? Right here, guys, before the break, also on your handout, we had cosine A plus B. That formula looked like this, just for a quick reminder. Looked like that. You guys agree? And that's the way this in the black looks. Therefore, what should the answer be? It should be this. It should be cosine of A plus B. Guys, A is 5 pi over 12. And add to it what? 7 pi over 12, that's B. That's what the formula says it should be. I think. Add them up. I think that's pi. Please help me here. Is it pi here, cosine? 12 pi over 12? Now, please tell me that takes me right back to the unit circle. What's the cosine, the x coordinate at pi? -1. You say, Professor, really? Are you telling me all that in the black is equal to this? That's what I'm telling you. All that's equal to a -1. Jeez. Now, I'm looking at this handout, because I'm gonna move to chapter 7. Come back to these formulas tomorrow. Oh, my goodness. Hang on. I'm scared. I see something on here that was, I'm looking at my time here, I see a problem on here that, oh my goodness. Has to be done, but it looks scary. You guys wanna be scared today, or wait till tomorrow? Give me a choice, you want to be scared right now and get this over with, get the scary part over with on this handout? Or should I move on into chapter 7, show you a brief introduction to chapter 7, he's scary tomorrow? Oh, tomorrow, you've been scared enough of this rain coming down, right? So you won't be scared tomorrow. Okay, I'll hold off, and I'll tell you which one it is. And who knows, some of my students may have had some experience with doing this. It's, letter C. And what I forgot to do on letter C, if you look at letter C, I should have placed parenthesis around inverse tan all the way down to inverse cosine. So you guys want to put parenthesis around that. Inverse tan all the way down to inverse cosine, all that should be enclosed in parenthesis, and that cosine should have been all by itself out front. That is the one that looks a little scary. So we're gonna hold up on that. You won't be scared yet. Okay? Guys, any concerns up to this point though? Anything at all? Now, I've got just enough time. Of course, you know I'm not quite finished with all this. TK, this is yours, I think. Remind me to finish that problem up tomorrow. Leave this. By the way, do I have any students interested in doing math? I mean, doing maybe some career that may involve math, or maybe, who knows, you'll be back here at SMC teaching math. I told you I have one of my students here teaching. That's all I learned. Anyone interested in teaching? But some of you guys, I think, are thinking about careers that may involve math. I know Arena, she's not with me today. She wants to go into physics, and she's got a lot of math to do. Okay. Somehow your career may involve that. I want to do this right quickly, guys. Part 2. Now, this is chapter 7. Brief introduction. I gotta watch myself here. Finally, they do this in your textbook. They finally go back to middle school and discuss trig with the right triangle. Not the unit circle. They finally go back. And when I mention trig, I'm sure many students say, oh, Professor, I saw some trig back in middle school or high school. And I remember, and I think you guys were using that word SOHCAHTOA, I didn't know what it meant. SOHCAHTOA, I thought it was, I thought they were calling you a bad name or something. I didn't know what it was. And all of a sudden chapter 7, it closed down the trig part of the course. They go back to that. And how do they go back? They're saying, well, take students back to middle school, because that was a good experience, and do this. And when I start this, you guys will remember, we'll go to a grid. What we did this. I had a unit circle to work with. I placed a point, let's say a point right here, and we'll label it XY. Real quick for you guys to save some time here. And we said by definition cosine is the X. Sine was the Y. Is that true? If this is a what type of circle? Unit circle. Is that true? Now they're saying, well, have students to still consider that, but let's connect and form an angle inside here. Like that. That has for coordinates X, Y. But now have students to please do this. Have them go back across the street to the middle school. We need to make a field trip. Let's see what they're doing over there. And drop a perpendicular down to the x-axis on that unit circle. And form, of course, a right angle. And place theta inside here. Now they made a right triangle. Now when I first introduced the trig to you guys for the unit circle, I may have dropped a perpendicular for a certain reason or not. They work with the circle itself, but not in regards to what we're going to do now. What they do, they redefine the 6 trig functions. Sine theta, if we're on a unit circle, we think of it as, by definition, that we work with, y. Now, they're saying, please have students think of sine. If you're using a right triangle, some students may know what it is. They change the definition a little bit, you're going to use a right triangle. Does anyone recall what it was back in middle school for the definition for sine on a right triangle? Just the length of the opposite side. Here we go. I'll just write opposite side, talking about length. And Joseph, what else? Hypotenuse, the length of the hypotenuse. What a word, hypotenuse. Opposite side of the hypotenuse. Now I know what the hypotenuse is. I think by now in math, I think, is that the side opposite the right angle? Is that this right here? Is that true, guys? And if I were on the unit circle, that is also the radius is at 1. So the radius of the unit circle was 1 that we've been working with all this time. Wait, hold on a second here. Okay. This is y, definitely. And the base is x. That makes sense. On this triangle. Now, Joseph, if I use your definition, it says opposite side or hypotenuse. Well, the opposite side is y, opposite the angle. So here's my angle. So opposite the angle is y, right? And then place it over the hypotenuse. And if I'm on the unit circle, the hypotenuse has a length of what? 1. Are we back to the old definition? If I'm on the unit circle, y over what? 1. Now they're saying, please, in chapter 7, have students to open it up, and maybe you're not on a unit circle. Maybe it's a larger circle. Or a smaller circle, not a radius of 1. So they open this up and say, just call this R. It's called radius. And then they're going to make their definition then, opposite side over hypotenuse. In my case, that would be y over R. You're hoping that R is a 1. That would take you back to the unit circle. In case it's not, there's my new definition. Number 2, cosine. We think of cosine, have been thinking of cosine. Unit circle is x. Now though, Joseph, I may need you again. Tell the class what you think from middle school. They gave us the definition for cosine back then. What? That they call it the adjacent side, side next to. Adjacent. Side. Over the what? Hypotenuse again?
Yes.
Okay. Wow. Okay, guys, let's go up to my sketch up there and see what this now looks like. The adjacent side, that means the side next to the angle. Well, that's considered x. So that's x there for the side adjacent. And the radius is, of course, r, and there's my definition, x over r for cosine on a right triangle. Adjacent over hypotenuse. Now, guys, I'm giving you the definition for one more. I know we're supposed to have 6 altogether, but why would I necessarily not have to give you the other 3? If I give you one more and have 3 of them, why would I not really save myself a little time, actually write the other 3? Are the other 3 just reciprocals of these 3? So my third one, my last one that I really need, is tangent. Here we go, we've been thinking of it like this. Tan is y over x, that's what we've been using. Now, tan, Joseph, do you recall what middle school says to do for tangent? Thank you, take the length of the opposite. We used to abbreviate it, save a little time here. Opposite side over what, the adjacent? We'll abbreviate. We have the opposite side over the adjacent. Now, looks like if I use my triangle, the opposite side has been identified opposite the angle as a y. The adjacent side, the side next to it, is x. So do I end up with y over x if I use this middle school definition? That's right, guys? Which really takes me right back to what we were accustomed to on the unit circle. That's what they're doing on the right triangle. We did unit circle first. Some of my colleagues, I think, go to the right triangle when they teach this course. I think they do the right triangle first and then go to the unit circle. I did it the way the textbook did it. Guys, those are the 3 major ones. Do I need cosecant? No, cosecant should be what if sine is y? Cosecant should be what? 1 over y. They are reciprocals. Cosine is related to secant. Secant should be the reciprocal, so secant should be what? 1 over x. And of course, this one, if I ask you for cotangent, reciprocal is what? X over y. And now you have these definitions on a right triangle. Can someone please tell me, remind me, I shouldn't even place this on the board. Can someone tell me, and I know you've seen it because students use that word. Well, no, they're not maybe even misspell it. If there is a spelling for it. Sokotoa. Does anyone remember what it was? It was an S? O-H? I'm trying to think what it was when the student tried to show me. Sokotoa, and a C? I think it's A-H. And then TOA. They were saying, Professor, that's the word that my teacher used. And that's the word we were using in the hallways when we were talking. I said, what? And I thought you were calling me a nasty name. You got rid of V for some reason. You failed that last quiz and you said, Professor, something on it. What does it mean? Help me out. Is it just initials trying to help you remember this? One of my students said, I don't know whether I had this thing written down right. I think they said S was for sine, and sine is opposite over hypotenuse. And then next, I didn't know this. C was cosine. Cosine should be adjacent over hypotenuse, which I think we said earlier, didn't we? And then the TOA, what a crazy word. TOA, T, tangent, and tangent is equal to opposite over adjacent. Would that help you guys remember this or not? It didn't help me. I don't know what they meant, but some students said that's the way they remember it, Professor. Can I use it? If that's the way you remember it, go for it. That really tells you all we did right here. Okay, oh boy, I got 5 minutes. Here's what we're doing in 5 minutes. And we set you up. Part 3. Here we go. You know, and I know, you're not middle school anymore. Those days are gone. I hope you enjoy them. Those days are gone, PK. So you're gonna move from that right triangle tomorrow, we'll set you up. And deal with a triangle that may look like, they label the vertices they call them. Triangle ABC that looks like that, and it's not a right triangle. It's called an oblique triangle. Does anyone remember what I have to do tomorrow as I introduce this? If that's triangle ABC, they call it oblique, it's not a right triangle, no right angle. Does anyone recall how they label the sides? How do they label the sides of the triangle? I have the angles. This is angle A, this is angle B, this is angle C. No, do it again.
I'm looking at the questions.
So what is it?
It's like,
There's a special way they label, if it's not a right triangle, especially not a right triangle. They label the sides with lowercase letters. And they're opposite the capital letter. So if they have angle A here like I have, then the side opposite over here, they label that as a lowercase a. To represent its length. If this is angle B, capital B, opposite it, in my case over here, that's a lowercase b. And of course down here would be a lowercase c. So they got the lower cases to represent the lengths of the sides opposite those angles. Woo! Joseph, before we close down, something quiz. Sure. Just throw it out there, see what you want to say. Can I say on this triangle here, Professor, are you talking about c squared equal to a squared plus b squared? You say call those sides lowercase c, a, and b. So could I say c squared is equal to a squared plus b squared from middle school? Professor, you keep on taking me back to middle school. What are you gonna do, Professor? Walk me across the street? Like a little, you know those little field trips you guys took, probably your teacher walked you across the street and was so careful with you? Yeah, I'm just taking my group across the street. Middle school. Can I say c squared is equal to a squared plus b squared? No. Why? It's not a right triangle. If it's a right triangle, you can use those letters. C squared is equal to a squared plus b squared if it's a right triangle. This is an oblique. So we got some issues tomorrow to deal with the oblique. Okay, guys. At least we did it.